So far, we've looked at how you could identify PSAT by just kind of directly plugging in your equations of state. For this final video for Chapter 7, I want to show you another approach which involves using departure functions. And so if you remember from Chapter 6, with the departure function approach, we could describe an intensive variable. So in our case, we want to describe Gibbs energy. We could describe it as the sum of two contributions, an ideal gas contribution and then a contribution that accounts for things that are non-ideal. In Chapter 6, we could derive an equation for the departure function of the Moeller-Gibbs energy, which is taking the departure function of enthalpy and subtracting off T S departure. And that gives us this equation. RT over V minus P dV. Okay? Where in this integral, for your pressure term, this is where you would plug in your equation of state. Okay? Alright, so that's just what the Moeller-Gibbs energy departure function is. Now, if we look at that in the context of our delta G, which would be G vapor minus G liquid, if we plug in the form up here, what we would get is, for the vapor phase, we get GIG plus GV departure minus GIG plus G liquid departure. Okay? And the reason for the ideal gas contribution, I didn't distinguish between vapor or liquid, is because if you remember, with the ideal gas law, because it's so simple, it actually can't predict phase transitions at all, right? And so, if you're talking about a vapor or you're talking about a liquid, for the ideal gas law, they're all the same, okay? And so what that means is that the ideal gas contribution between the vapor and the liquid phases are the same. And so if we're looking at the difference between them, the ideal gas contribution, those things are just going to cancel one another out. And so if we look at delta G using the departure function approach, we find that our delta G actually just ends up being the difference between the departure functions of the vapor phase and the liquid phase. Okay? And if we apply our equilibrium criteria, we know that delta G at equilibrium is equal to 0. And if delta G is just equal to GV departure minus GL departure, that means that at equilibrium, the departure function for the vapor phase is equal to the departure function for the liquid phase. All right? And so that's, using the departure function approach, we could also define another criterion for equilibrium. All right? And so we could set the departure functions themselves equal in order to identify equilibrium. But there's actually another approach that uses the departure functions that people follow. And so instead of just looking at the departure functions themselves and setting them equal to each other, what people do instead is they calculate something known as fugacity. Okay? And so equivalently, equilibrium can be defined in terms of fugacity. Okay? Alright, and so fugacity, which is abbreviated commonly as F, it's just defined like this. Fugacity is going to be your pressure times the exponential of your g departure function divided by RT. You know, that's just mathematically what fugacity is defined as. Okay? Now, as far as physical meaning of fugacity, the way I think of it, and the way I encourage you to think of it, is that it's just a non-ideal version of pressure. Right? Because if you're dealing with an ideal gas, by definition, your departure function would be equal to 0. Therefore, your fugacity would be equal to p times the exponential of 0. Exponential of 0 is 1, and so you would just end up with your fugacity being equal to pressure. But if you're dealing with a non-ideal fluid or gas, then, so if your departure function is not equal to 0, then the fugacity deviates from pressure. Okay? And in any case, what you could do is you could just rearrange the fugacity equation so that you have your g departure is equal to RT natural log of F over pressure. Okay? And so, at equilibrium, we know that the g departure function for the vapor phase, which if we write in terms of fugacity is this, we know that that's equal to the departure function for the liquid phase, which is equal to this. So we have this is equal to this. The RT's cancel. We could take the exponential of both sides, and then the pressures cancel. And so what we find then is that at equilibrium, F of the vapor is equal to the fugacity of the liquid. Right? And so that itself is another criterion for equilibrium, is that the fugacity of the two phases are equal to one another.